Okay, let me begin with a word of prayer. Dearly Father, we thank you for this day again. I thank you for this class. We thank you for your creation that you've made for us to enjoy, and pray that we glorify you in what we do, and that this just be a good use of our time, Lord. In your name I pray, Lord Jesus. Amen. All right, so I want to talk about variational calculus. And admittedly, this is really just an invitation to a deeper study, okay? Because a proper course in variational calculus, you can talk to Dr. Sprano. He actually had a course. It's funny. I've probably done a lot more variational calculus than Dr. Sprano, but I haven't had a course in it, which is kind of ironical, to use a Dr. Wangism. Although ironical is a legitimate word, it turns out. But in short, like, you could take a whole class on variational calculus, and variational calculus has been with us since the since the dawn of calculus, and but yet it's kind of fallen out of the main calculus sequence these days, right? I mean, if you look back at the calculus books of the early 19th century, you'll find that there's a chapter on variational calculus at the end. And like the Bernoullis studied problems of variational calculus. Galileo was trying to solve a problem of variational calculus. I mean, it's from the start, it's been there. But for whatever reason, it's kind of been relegated to a much, like, not many people get to see variational calculus, right? And oops, I really should have printed this out. Oh well. So let me talk about the variational problem, and I'll probably add some pictures to this. And so what we're going to consider is J is the action. It's a functional, and J is going to be a mapping from some function space to some function space, and it's the integral of some function f, which we call a Lagrangian. So like J of y is going to be equal to, say, the integral from x1 to x2 of f, which is going to be a function of y, y prime, and possibly x dx. All right. So we suppose that f is given, but y is a variable. And suppose we're given a function y star and f naught and another function eta, such that eta vanishes at the endpoints. So we consider y star an element of f naught and eta, all right, a mapping from, let's say, x1, x2 to the reals, all right, such that, eta of x1 equals to eta of x2 is equal to 0. All right. Then, oh, come on. I guess I got to plug my computer back in. Sorry, I forgot to print this before class. It's cramping my style here. Then we can look at a whole family of functions indexed by a real variable alpha, and we'll relabel y star by to be the matching 0, and like here it is anyway. So we can look at, I'll draw a picture of this in just a second. So we can look at y of x comma alpha, all right, equal to, let's say, y star of x plus alpha times eta of x. All right, so like, for instance, y of x comma 0 would just be equal to y star. All right. Now, I guess I should be clear. What is this f naught? That's what I've not been clear enough. But with this definition, y of, let x, this, is an element of f naught. Now, f naught, what is f naught? I haven't, f naught is just, these are functions whose graphs contain a given pair of points. All right, so like the picture is something like this. We got a point x1, y1. We've got another point over here, x2, y2, okay? And so for a function to be in this f0 space, I'm insisting that its graph go through these 2 points. We're considering such functions, all right? So, of course, somewhere in here, we can have y star, all right? But as the alpha varies, right? As alpha varies, you're adding, you know, this eta function, right? An alpha times eta, and so you can kind of envision it, you know, I don't know what it looks like. It could do kind of wacky thing, whatever, but it comes back, right? And then if that's let me not commit to that picture, because this, if I try to draw an index family of this, nothing, it's going to be hard for me, okay? So instead of that, let me do something a little bit easier to graph, like, you know, maybe this is alpha, maybe this is like this guy, maybe that's y of like, you know, x comma, I don't know, 0.2. That's equal to y, all right? Like it's the alpha equals to 0.2, right? And then maybe alpha equals to 1 is like up here somewhere, you know? Maybe that's y of... Now if I was doing it correctly, of course there should be some regular, you know, pattern between, because I'm just adding a scalar multiple of the eta function, right? That's what this formula does. It just adds a multiple of eta at each point. We're just adding. But the thing is, the eta is fixed at the endpoints, right? So it's clear enough that this whole family of functions, it does fit in the space f0, right? Okay. So we define a variation of y. So definition, the variation of y is delta y, delta y equal to alpha n of x. Well, eta of x, okay? In other words, another picture you could draw would just be like, you know, here's your y star, right? And then up here is your y plus the variation of y, okay? And you're just allowing that variation to be whatever along the path, right? It could be whatever. This eta is completely arbitrary, but we're indexing it by alpha for a fixed eta, all right? And so this means then that we can re-express, see this, with this setup, we can meaningfully express the action, this is the action, okay? Action is typically the integral of Lagrangian, but we can express the action as a function of alpha, right? So if you look at this, what would be j of alpha? Well, j of alpha would just be like integral from what, x1 to x2 of f of what? F of y of, you know, x comma alpha comma, what's y prime? Well, let's say y prime of x comma alpha, right? The differentiation is taken with respect to x there, and then, well, x, of course. All right. And so here's what I say. I say it is intuitively obvious that if the function y star is an extremum of the functional, well, let me ask you, if y star is actually, if we say, okay, now suppose that this y star is actually an extremal point for the action. If that maximizes or minimizes the action, right? Then what should we have about alpha? So that happens when alpha equals to 0, right? Alpha equals to 0 right here. We get y star, right? So what should be the case if I calculate like dj d alpha, right? And I look at, alpha equals to 0, what should that give me? I mean, look at it. J of alpha is a real valued function of a real variable. Now it's running through a bunch of functions of several variables, right? But with this setup for a fixed eta, yeah. Yeah, it should be 0, right? Because it should be an extremum for this function of alpha, the real variable. So this should be 0, right? I mean, if this is the extreme function for the functional, then it should be the extreme for no matter what choice of eta I pick. Whatever choice of eta I pick, if I look at all functions near it, the value of this action for all functions near y star, it shouldn't matter if I'm sampling from all the ones that are eta related, or if I was to pick a different eta, say eta 2, if I was look at all of the adding eta 2, it still should be the case that y star is the maximum close to whatever. If I look at some family of functions which is close to y star, it should still be the case that it's maximum there. All right, you see I'm waving my hands a lot. So this is actually what? So we need to calculate the partial derivative with respect to alpha of this thing, right? With this dependence more explicit in the step above. So what are we going to do? Well, first of all, commute the order of the integration and the differentiation, all right? And so what do we have? Partial alpha of that, right? And I'll write back in the functional dependence y of x alpha, y of x alpha prime, if you like, and x. Okay, so great. So how do you differentiate a function of several variables? Well, we have the chain rule, right? We have the chain rule. And so the chain rule here looks like the following. It looks like integral from x1 to x2 of partial f partial y, partial alpha, all right? Plus partial f partial y prime, partial alpha, all right? And then plus partial f partial x, partial x, partial x. I guess it's partial x partial alpha, all right, dx. Because those are the three variables for f. But partial x partial alpha is by assumption 0, right? There's no x, we're not varying, the x is not being varied under the variation at all. So this is 0 by construction. All right, there's nothing to think about there. But what about the others? What's partial y partial alpha, and what is the other one? So okay, so there we just need to go back to the setup right here, right? So what's partial y partial alpha? Eta. So this is literally eta. What's partial y prime partial alpha? Well, if we differentiate this with respect to x, what do we get? Well, we get y of x comma alpha prime equals to y star prime of x, right, plus alpha eta prime of x, right? So if I differentiate that with respect to alpha, I get what? Eta prime, right. And of course, that is specifically d eta dx. So let me write it out. Now, we're up against the integral from x1 to x2 of partial f partial y eta plus partial f partial y prime d eta dx, okay? Dx. All right, now the eta, keep in mind that the eta here is essentially arbitrary. So we'd like to, if we could get eta and factor it out, since eta is arbitrary, if we can see that this has to be 0 with respect to arbitrary eta, then by golly, whatever is multiplying that eta, it's got to be 0. We're almost there. I mean, we've got this eta sitting here, but how do we get the eta out of the derivative? How is that accomplished? See, this is a muscle math majors don't flex enough, but it's called integration by parts. So, because, let's look at it this way. d dx, right, of eta partial f partial y prime, what's that equal to? Well, it's equal to d eta dx, right, partial f partial y prime, plus what? Plus eta, right? I'll do it down here. Plus eta times d dx of partial f partial y prime, right? By the product rule, because they're both functions of x. So if I use that over here, I've got myself integral from x1 to x2 of like partial f partial y times eta, all right? And then I want to trade, see, I've got this one right here, right? That's here. So I'm going to trade that for a derivative of eta times partial f partial y prime, all right, minus eta times d dx of partial f partial y prime, all right? Okay, so let's, oh hey, look, integral of a total derivative, so what's that? Well, that's eta of x times partial f partial y prime evaluated at x1 and x2, right? Plus the integral from x1 to x2 of partial f partial y minus d dx of partial f partial y prime all times eta of x, of course, dx. But what did we assume about this variation, this eta of x? Remember, we assumed that it's 0 at the endpoints. So provided that partial f partial y prime is not terribly badly behaved, right? Well, anyway, this is 0, so that just gone, right? And then since that has to be equals to 0 for arbitrary eta, right? This whole setup happens for one eta, but it happens for any choice of variation. Completely arbitrary eta. That means, for fixed f too, right? That means that whatever this is, this has to be equal to 0 in order for that to be for this to be an extremal action. So for y star to be the extremal path, it must be the case that what I just underlined in red must be 0. And so for that reason, we insist that partial f partial y minus d dx of partial f partial y prime is equal to 0. That right there is the most basic case of the so-called Euler Lagrange equations. So it's pretty simple. If you can write an action as the integral of a Lagrangian, then the extremal path has to satisfy the Euler Lagrange equations. Now, it's not at all obvious whether it's a min or a max, right? That requires further study, which we never do in here. But yeah. So the reason it's called the Euler Lagrange equation is because both Euler and Lagrange derived these. As I understand it, Euler did some monstrosity where he took the hypothetical path that was being extremized or maximized between the 2 points, and he introduced a finite set of intermediate coordinates, like points of the intermediate path, and then he solved the optimization problem for that set of many, many variables. And somehow, from all that, found these.
But what I've heard is that Lagrange didn't
Holy cow.
anything.
Lagrange.
All of Lagrange's work was done by Euler, and Lagrange paid Euler for it.
Really?
Like the Lagrange.
So you think all of Lagrange's work is actually Euler's work? I don't know if I believe that.
Or I'm thinking maybe of L'Hopital.
Oh, L'Hopital. Yeah, L'Hopital.
That's the one.
Maybe L'Hopital. Yeah, L'Hopital had that very popular. I don't know. I mean, his calculus book had. Yeah, like L'Hopital's rule is not really his. It's probably like, yeah, Euler or maybe a Bernoulli or something. We don't know. I don't think we even know. Like if you asked who found the chain rule first, you could not find you could not find an authoritative answer on that, because like a lot of these basic rules of calculus, they were known to Newton, they were known to Leibniz. Some of them were known to their teachers, but the difference, of course, was that Newton and Leibniz understood the totality of what was going on and convinced other people it was worth doing, right? So even though, yeah, like I think Isaac Barrow was that Barrow? I'm not sure it's Isaac, but like Newton's professor studied tangents, like his whole career I think was tangents. But I don't think he understood the fundamental thermocalculus. I mean, it's right in front of him. Surely he must have understood a case of it or something, but the ubiquity of the theorem. But anyway, so Lagrange, on the other hand, actually, this notation is from Lagrange. So the variational notation is from Lagrange, and that figures heavily into his so-called variational mechanics. So like the way we're still doing classical mechanics, the best way is due to Lagrange. But now I won't derive it, but if instead of having just one variable, you have many, basically the same derivation goes through, and you just get a different Euler Lagrange equation for like every variable that you have. Let's see if I can show you another example here. So yeah, like on page 165, I show what this. So all right, so when I took physics, right, I was a physics major, and you got to understand, there's a semester in my physics/math undergrad where on the one hand I'm taking real analysis. All right, I'm taking real analysis in one class. I'm taking like junior level mechanics, I think, in the other. I think this is, I may have my semesters mixed up in the storytelling, but just bear with me. So on the one hand, and this is not how we did it in my mechanics class, okay? When we talked about variation in physics, we did something like this. We said, okay, so S of like Q, and maybe we did Q dot. It's something like, like integral of the Lagrangian of say Q, and there's a bunch of these, so the Qi and it's a Qj and Qj dot, all right, and then possibly T dt. So I guess technically it's like Q sub j and Q sub j dot to be fussy. Well anyway, they probably wouldn't have written that there. They probably just like this. And they're like, okay, well, Hamilton's principle of least action says that the variation of the action is equal to 0. All right? That's what we said in physics. And then we're like, and so you just take the variation of the integral. So if you take the variation of the action, you've got the variation of this integral. All right. And then they're just like, okay, so you can, you commute the order of integration and variation. You got the variation of L. But then, of course, that is, partial L, partial Q, partial L, partial QJ, let's say, variation, rats. Oh, I'm sorry, I'm being too greedy. Let me just stick back with Y. I'm trying to make a point here, and I'm making it too ugly. My bad. All right, so then like the variation of Y is just going to be, like partial L, partial Y, variation of Y, plus partial L, partial Y prime, the variation of Y prime, all right, and then plus like partial L, partial T, the variation of T, all right. But we're only considering a variation in Y. The variation in T is assumed to be 0. It's just like that's 0. And then they're just like, I'm trying to remember how it goes. They're just something like, they just say something like, oh, so, if you take the variation of partial L, partial Y prime, and with Y prime, right? Well, then you just get, the variation of drat. Just a second. I've forgotten how to be confused. Well, you got the variation of dy dx. Yeah, okay. Yeah, my bad. So then what I was told in my junior level physics class is that the variation of y prime, well, that's really just the variation of dy dx, but you can just commute the variation in the derivative. So that's really just d dx of the variation of y, right? And at that point, we're kind of back to where I was in my other calculation, because we got partial L, partial y prime is like, the variation of y prime is partial L, partial y prime d dx of the variation of y, right? And then we just say, oh, well, that's d dx of partial L, partial y prime times the variation of y minus d dx of partial L, partial y prime times the variation of y. So then I trade, I do integration by parts. I trade this right here, which is here, for these two guys. And that gives me integral of like partial L, partial y, minus d dx of partial L, partial y prime times variation of y dt plus the integral, well, plus partial L, partial y prime, variation of y evaluated, at the n times, n times. Maybe I should have an integration over x or something. No, I mean, it's done for time, but and they're like, oh, well, and this has been set up with there's a story time that leads up to this. Okay, it's not just done quickly. It's done This is not a slow event in my physics class. This takes like 20 minutes to go through, okay? And we're like, well, the way we've explained it, this goes to 0, but the variation is arbitrary, therefore this must be 0, or the Lagrange equations. This is the argument which is given in physics. But this was very upsetting to me, because I'm like, what do you mean you just commute the delta and the d? What is the delta? Well, it's a variational derivative. Well, what is a variational derivative? And then they just start talking about virtual functions and things. But the actual like analysis of it, I've just showed you on the other board. It's actually not that complicated. And some of these things I believe I got out of, this is a nice book, Arfken. I think Arfken is the name of the book. Arfken. I think that's where I found some of these things. Like it's a like mathematical physics book. But anyway, that of course can be made more rigorous in a graduate class of variational calculus, and because we're not paying enough attention to like what's the nature of the function space and how you set up that variational derivative, all those things. But that's pretty close. That at least there is some understanding of how it is that the I didn't just magically commute the variational derivative and the derivative in that derivation over there. So my point was, at the same time I'm taking this classical mechanics class where we're doing this kind of stuff, like I'm taking a real analysis class where I'm losing points because I've said C is an element of the reals at the top of the page, but I haven't emphasized it when I used it, that A is less than B and B is less than C implies A is less than C. And then she's like, but you didn't say that C was a real number. And I'm like, I said it at the top of the page. She's like, well, you should say it here to emphasize. Just like, you realize we're differentiating infinite functions in my other class. Like we're doing stuff like this. What's the derivative with respect to x of the unit step function? Well, it's the direct delta function, of course. Like, we're doing this. This is 0. It jumps up here to 1 like that. This is y equals u of x. This thing is the direct delta function. It's actually not a function. It's a distribution. It has a spike like that. That's y equals delta of x. It's technically infinite at 0. So we're taking the derivative of a discontinuous function and we're saying it's equal to an infinite function, which, by the way, has area of 1 under that spike. That's how the direct delta function is defined. And it's hard to be a double major in math and physics sometimes. You feel the hypocrisy of the two fields contrasted. It's sometimes like too much. Now, of course, the error was, of course, all on the part of the physicist. Well, that's not true. I mean, sometimes you have to gloss over some details to make progress, right? All right, in that note, let us go on. So let me talk more about physics. Let me just give you some of like the most famous examples of this, all right? Let's see here. Of course, you can solve like the geodesic problem, like, closest point on a surface. You could do something like that. Let me see if I can find that example. I think in the notes I have like the minimum surface area problem. I'm not too fond of that one. The Berkristochrone that's a famous problem. It's you've got a particle slides freely along a curve from one point to another under the influence of gravity. We take y to be the vertical direction. What's the curve of quickest descent? So let me talk about that for a minute here. I'll show you how to set it up. This one's a little bit kind of a one-off. This isn't really, I wouldn't say, it's not exactly, well, I mean, it's a physical example, but this isn't physics, if that makes sense to you. So if we have something that's sliding freely under gravity, so this is the Berkristochrone, I can't spell it. That is almost certainly spelled wrong, but the basic thing is you're starting at the point x1, y1, and we're letting it slide to the origin just to keep things simple. All right, x2, y2 equals to the origin. All right, so there's some mass, some bead with mass m that's sliding down this wire, all right? And the question is, what's the curve of quickest descent, assuming that it slides without friction, all right? But nevertheless, it's not free fall, right? It's not, it has to go along this arc, so it's forced to go along this curve. So, there's one solution we don't need variational calculus for, right? If x1 is equal to x2, that's very easy. But so we assume x1 is not equal to x2, and we're trying to minimize time of descent. And it's falling freely under the influence of gravity, which means that we have conservation of energy. We've got like, how's it go? 1/2 mv squared is equal to mgy minus y1. So, for example, when y is equal to y1, we're starting from rest, okay? We're starting from rest. See that? If you put y equal to y1 in this formula, we get 0 for the potential energy term, equal to 0 for the kinetic energy. So this is just coming from 1/2 mv squared plus 1/2 mv squared minus mg. Excuse me. Should that be y minus? Is that the right way? Man, let's try to believe that. Yeah, there's a typo there. It's a typo in my notes. Goodness gracious. That's annoying. What would conservation of energy say? 1/2 mv squared, right? Plus mgy1, plus mgy rather, is equal to mgy1. So this would be the energy at some point is slid down a bit, and that's the initial energy. The initial energy is just potential. So when you solve that, you get y1 minus y, not the other way around, okay? All right, great. And we're trying to minimize the time of descent, right? So first of all, you notice that, so this is the problem that Galileo tried to solve, by the way. He thought the answer was a parabola. He's wrong. It's not a parabola, as it turns out. So you can cancel the m, right? And you've got v squared is equal to 2g y1 minus y, right? But what is v? Well, v is ds dt squared. So I can solve that for ds is equal to what? I can solve this for ds is equal to the square root of 2g y1 minus y. Oh, I'm trying to solve for dt, right? My bad. I was like, I thought I got a reciprocal. Well, no duh. So dt is, ds over the square root of 2g times y1 minus y, right? And we're trying to minimize. So how do we? What's the functional we want to look at here? We want to integrate that, right? We'd integrate that to get the total time of the descent. That's the way to think about this. And so specifically, and we can rewrite what's ds in terms of, I guess we're going to do it in terms of x, integration over x, right? So you notice that ds is also the square root of 1 plus y prime squared, right? dx. That's the formula for arc length in terms of x. All right, so then, all right, so great. We then what we're interested in then is, you know, our action, if you will, is j of y. It's the integral. Apparently, I guess we can do from 0 to x1 of the square root of 1 plus y prime squared dx over the square root of 2g y1 minus y. Now to make this problem nice, you don't want to look at the regular Euler Lagrange equations. You want to look at what are called the modified Euler Lagrange equations. The modified Euler Lagrange equations, and you can just prove like through chain rule or something. I forget the details actually at the moment, but you can prove that partial f partial x minus, so like the Euler Lagrange equations imply that partial f partial x is minus ddx, big parentheses, of f minus y prime partial f partial y prime that's all equal to 0. Now it's probably a good exercise to convince yourself why it is that that's equivalent to the Euler Lagrange equations. So this is allegedly interchangeable with the Euler Lagrange equations, which in this context look like partial f partial x minus ddx of partial f partial, wait a minute, that's not the Euler Lagrange equation. In this context, the Euler Lagrange equations would be partial f partial y, my bad, partial f partial y minus ddx of partial f partial y prime is equal to 0. Allegedly, if you differentiate this, you can get to here. It's probably like, so when you differentiate this, it's a function of y, y prime, and x. So one of those terms is like partial f partial x dx dx, that cancels this. And then the other two terms are like partial f partial y, y prime, and partial f partial y prime, y prime prime. So, well, anyway, I've worked this before. It's not a hard exercise. I'll let you try to figure that out, okay? Anyway, so if we have that, that's super nice. Now, notice what I have right here. This is my Lagrangian, as it's called. So the term Lagrangian is more general than its application in physics, but in physics, the Lagrangian specifically means, under usual circumstances, the kinetic energy minus the potential energy. All right, so we'll look at that in a bit here, but let's finish this problem. So for this one, there is no x dependence. All right. So notice there's something a little bit subtle here that'll confuse you as you're an introductory math student especially, which is like, wait a minute, you mean there's no, but there's a y. Y is a function of x, and y prime is a function of x. No, but in this world, we're treating x, y, and y prime as independent variables. So the truth be told is what you're doing is you're taking your problem on Rn and you're lifting it up to a corresponding problem on something called jet space. Jet space is a formal manifold which takes like a path, its derivative and its higher derivatives is actually independent variables. You solve the problem up there and you project back down. That's actually the mathematics of what's going on, something called jet space. And physicists do this, but they don't admit they're doing it. They just make rules, which is like if the student says, but y is a function of x, and you're like, no, you don't do that. You just don't do that. And that's enough, because they're physics students. They will accept your authority as a professor that you don't do that. And then it becomes the tradition of the physics community, and that is how it's done. So, but if you ask enough mathematical questions, eventually they'll send you to the math department, is what I found. So go figure. Anyway, this is 0. That's f. So what we have is like d dx of, this thing. I'm just going to write it as a single square root, okay? That monstrosity, right? Minus y prime. And, can you tell me how to differentiate that with respect to y prime? I guess you just got.
The whole thing at the bottom.
Yeah, the whole thing on the bottom just rides along, right?
Yeah.
So we've got like a 2 square root of 1 plus y prime squared, right? Times the square root of that, right? And then upstairs, we've got ourselves a 2 y prime. That's it, right? Yup. Mm-hmm. Yup. Yup. Mm-hmm. Then what? So if the derivative of all this mess is equal to 0, right, that means that this is a constant. Which means that you can write the square root of 1 plus y prime squared minus y prime quantity squared. And rats. Oh, to make a common denominator, sweet. Square root of 1 plus y prime squared, right? We like our denominators to be common, not to be vulgar, but it's how we do it. Let's see here. You ever think about that? Common denominators. It's a vulgar denominator. Let's see here, because it's, 1 plus y. I think most of my college algebra students would agree. Common denominators are vulgar. That's equal to a constant. But what is this? See that?
Yeah.
That gives us just 1 over the square root of, so we have 1 over the square root of 2g times y1 minus y, right? Is equal to a constant times the square root of 1 plus, dy dx squared. Let me see how do I navigate these shark-infested waters. Oof, what have I done? Yowzers. Oh, okay. Yeah, same thing. Huh. Oh, dummy. Me, not you. So, all right, wonderful. Let's take a step back to here. So what this gives us, of course, is that, and if I follow my notes, I write that as 1 over k because that's convenient. And so this all in the top simplifies to what? 1. 1. So flip it, square it, and we've got k squared is equal to 2g times y1 minus y times 1 plus, I'll write it as dy dx squared. Then what? See, this is the thing about variational calculus, is that the Euler Lagrange equation part of it's simple enough. But solving the Euler Lagrange equations, well, that introduces you to a whole new world of substitutions and just non-standard calculus that you maybe have never seen before. And that's what we're currently in the middle of. So we solve for dy dx there. Solve for dy dx, what do we get? If we solve for dy dx squared, that gives us what? We've got like k squared, right? Minus 2g y1 minus y. So I'm just subtracting this piece to the other side, right? But then I'd have this times that, so I have to divide by 2g times y1 minus y, right? And then what? So what you're looking at then is essentially something of the form, so I let a equal to y1 and b equals to k squared minus y1. A equals to y1, b equals to k squared minus y1. With that adjustment, we have dy dx equal to, golly, why don't I, what happened to the g? Where'd my g gone to? Just a second, how did the g go away? Oh, I absorbed the g. So, absorb the g into the k, all right? You see that? I've redefined k to suck in the g, is what I did. Physicists do this kind of thing, it's annoying. Essentially, that amounts to g being equal to 1 here, okay? And okay, so then what? We have b plus y over a minus y. If I did it right, b plus y over a minus y, plus or minus the square root of that. So b like k squared minus y1. Well, there's a 2y1 there though. Did I get rid of that 2 too? Oh, I should have absorbed the 2 into here as well. So like that 2 is not there either. So sorry, this k squared, let me call that k bar squared. So k bar squared is technically equal to k squared over 2g, I believe. I mean, we can do that. And with that, then we're up to dy dx is equal to plus or minus the square root of b plus y over a minus y. All right. Can you solve that? All right, so we got dy dx is plus or minus the square root of, what was it? I've already forgotten.
A plus y over a minus y.
A plus y over, is it b minus y?
A minus y.
I definitely should have a b on one of those and an a on one. So b was,
Sorry.
oh,
B on the-
okay, so b plus y over a minus y.
And doing with the x to the other side.
Right, so yeah, that's going to give us like dy over the square root of, b plus y over a minus y equals to plus or minus dx. And then we can integrate that. The integral is not trivial, but after some work, this has solution x equals to a plus b over 2 theta plus sine theta. All right, minus d. And y is equal to a plus b over 2 times 1 minus cosine theta minus b. So that actually is the solution to the Brewster-Crone problem. And what that is a cycloid. The curve is traced out by a wheel, a point on a wheel as it traveled. And the time of descent, it turns out the actual time of descent works out to simply t equals to pi over 2 square root of y1 over 2g. Now I think I've actually seen this worked out in my mechanics class, and I think it took us about a week to work out this problem. This is a, not a trivial problem by any means. All right, so my next section here, section 8.5, is Euler Lagrange equations for several dependent variables. And basically the derivation goes through just the same. You just get a different, you get a new set of Euler Lagrange equations for each dependent variable, right? So I just want to show you a few much easier examples to end class today, or I think I started late, so. Oopsie. Forgot to, it's okay, I didn't derive anything, I just pulled things out of my hat. So yeah, we still got about a little bit more than 15 minutes left and then I'll stop. But all right, so in physics, the Lagrangian, we use the kinetic energy minus the potential energy. So like the kinetic energy, T, is 1/2 mv squared for a single particle, all right? And for a single particle, we have options. See, we could write that as 1/2 m r dot squared plus r squared theta dot squared. Way to be weird, I led with the polar coordinates. Or you could do 1/2 1/2 m x dot squared plus y dot squared, right? You could do like that. That would be the formula for two-dimensional motion, either in polar or Cartesian coordinates. There's the formulas for speed. Now potential energy, that depends on the problem. Okay, so like, I guess this is example 3. I guess the Brewster-Crone was example 2, wasn't it? I've forgotten. Was that example 1?
Probably.
Yeah, I guess it was. So I guess it makes this example 2. So how about a free particle? What's a free particle? Well, a free particle is simply one where, the potential energy is 0. So there's no force involved, it's just out there on its lonesome.